Hello, this is not your chem tutor, and in this video, I will teach you about partial pressure and Dalton's law. But before you continue this video, make sure you are familiar with the topic of ideal gas law, specifically the ideal gas equation, because later on we will be using the ideal gas equation to solve some problems related to Dalton's law. So as usual, in the end of my video, I put some examples so we can practice some calculations. Let's start by defining gas pressure. In general chemistry or in basic chemistry, we usually associate pressure with gases. So gas pressure is the force exerted by a gas on the walls of the container. So to better understand this, let's have an illustration. So for example, you have here a closed container. Now inside the container are gas particles. So each circle is a gas particle. Now we know that gas particles are mobile, which means they move around inside the container. At some point, the gas particles will hit the walls of the container. And when they collide with the walls of the container, they will exert a force on that area. For example, this gas particle will exert a force there, here, and then here. Now, this force exerted by the gas particle on the walls of the container is what we call the gas pressure. Now that you already have an idea on what is gas pressure, let's move on to partial pressure. So in a mixture of gases, the pressure exerted by each individual gas is called the partial pressure of that gas. So again, to better understand this topic, let's have an illustration. So let's say you have again a closed container. And inside the closed container, you have two gases. So the first one is represented by these red circles. So these red circles are the particles of gas A. Also, you have these blue circles. And these blue circles represent the particles of gas B. So these particles move around inside the container and eventually they will hit the walls of the container. So the red circles will hit the walls of the container. So that means gas A exerts a pressure. So the pressure exerted by gas A alone is what you call the partial pressure of gas A. Or in symbol, that is P subscript A. At the same time, the blue circles also hit the walls of the container. So gas B also exerts pressure. And the pressure exerted by gas B alone is what you call the partial pressure of gas B. Or in symbol, that's P subscript B. So that's how you explain partial pressure. Now that you have understood what is partial pressure, let's move on to Dalton's law. Dalton's law is actually a very simple law. It just states that in a mixture of gases, the total pressure is the sum of the partial pressures of each gas. So in equation form, that is PT or P total equal to the sum of the partial pressures. So we have P1 plus P2 plus P3 up to Pn, depending on the number of gases in the mixture. So let's have again an illustration so you can better understand Dalton's law. So again, we have a closed container. Now inside the container, we have these red particles. This represents gas A. We have these blue particles. This represents gas B. And we have these yellow particles. This represents gas C. Now, gas A exerts a partial pressure. So, partial pressure of A. Gas B also exerts a partial pressure. So, partial pressure of B. Gas C also exerts a partial pressure. So, that's P subscript C. Dalton's law says that the total pressure, or PT, is equal to the sum of the partial pressures. So PT is equal to PA plus PB plus PC. Now let's say PA is equal to 5 atm and PB is equal to, let's say it's 3 atm, and PC, let's say it's 1 atm. So using Dalton's law, the total pressure is equal to 5 atm plus 3 atm plus 1 atm. And if you sum the three partial pressures, you will get 5 plus 3 plus 1, that's 9 atm. So the total pressure is 9 atm. And that's how you use Dalton's law. Okay, let's proceed to our examples. We have example 1. A mixture contains oxygen gas, nitrogen gas, and carbon dioxide gas. Oxygen gas exerts a pressure of 0.150 atm. Nitrogen gas exerts a pressure of 0.780 atm. And carbon dioxide exerts a pressure of 0.060 atm. Calculate the total pressure. Since the question is asking for the total pressure and we are given the partial pressures, we will be using Dalton's law. So again, Dalton's law says that the total pressure, or PT, is the sum of the individual partial pressures. So we have three gases, O2, N2, and CO2. So the total pressure will be the sum of the partial pressure of O2, partial pressure of N2, and partial pressure of CO2. So the equation is very simple. We just need to substitute the values. According to the problem, the partial pressure of O2 is 0.150 atm plus the partial pressure of N2 is 0.780 atm plus the partial pressure of CO2 is 0.060 atm. Now, if you add the three partial pressures, 0.150 plus 0.780 plus 0.060, this is equal to 0.99 atm. So this is the answer to the first question. Now let's move on to example 2. A mixture contains neon, argon, and xenon. The total pressure is 760 torr. If neon and argon exert 150 torr and 300 torr respectively, what is the partial pressure of xenon? So again, we will use Dalton's law. P total is equal to the sum of the partial pressures. We have three gases, neon, argon, and xenon. So the total pressure is equal to the partial pressure of neon plus the partial pressure of argon plus the partial pressure of xenon. According to the problem, the total pressure is 760 torr. So you put 760 torr. The partial pressure of neon is 150 torr. And the partial pressure of argon is 300 torr. The partial pressure of xenon is not given. It's the missing one. So you just put PXE. So 760 torr. You can add 150 plus 300 torr. That is equal to 450 torr. Plus the partial pressure of xenon. So to solve for the partial pressure of xenon, you will move 450 torr to the left side and it becomes a minus. So 760 torr minus 450 torr is equal to the partial pressure of xenon. And if you solve this in your calculator, 760 minus 450, that is equal to 310 torr. So the partial pressure of xenon is 310 torr. That is the answer to example 2. Now let's move on to our last example, example 3. A 2-liter vessel contains 0.5 moles of argon and 1 mole of neon at 25 degrees Celsius. What is the total pressure of the system? Now, actually, example 3 has two solutions, and I will show you both solutions in this video. The first solution needs two formulas. First is the ideal gas equation, PV equals nRT, and the second one is Dalton's law, which we just discussed a while ago. Now, if you read the problem does not give us the partial pressures. Instead, it gives us the moles of the gases. So we have 0.5 moles of argon and 1 mole of neon. So the first step you need to do is to actually solve for the partial pressure of argon and the partial pressure of neon. So how are you going to do that? We will use the ideal gas equation. This one, PV equals nRT. If you rearrange the ideal gas equation to solve for the pressure, the equation becomes pressure is equal to nRT divided by the volume. So for the partial pressure of argon, that will be the moles of argon times RT over V. For the partial pressure of neon, that will be the moles of neon times RT over V. Now let's start with argon first. The moles of argon according to the problem is 0.5 moles. We know that R is 0.0821 liter atmosphere per mole Kelvin. And then the temperature according to the problem is 25 degrees Celsius. But we know that in ideal gas equation, we need to convert Celsius to Kelvin. So how do we do that? Again, we just add 273.15. So 25 plus 273.15, that is equal to 298.15, and the unit will be Kelvin. So this one is our temperature. So you put that into the equation, divided by the volume given in the problem is 2 liters. So if you see how the units will cancel out, moles will cancel, Kelvin will cancel, and then liters will cancel. So what is left is ATM, which is the unit of pressure. And if you solve the partial pressure of argon, grab your calculator, that's 0.5 times 0.0821 times 298.15 divided by 2. And that is approximately equal to 6.12 atm. So that is the partial pressure of argon. Now let's move on to the partial pressure of neon. So we will be doing the same thing. So this one is equal to the moles of neon is, according to the problem, 1 mole. The value of R is 0.0821 liter atmosphere per mole Kelvin. And the temperature, again, is 298.15 Kelvin divided by the volume, which is 2.00 liters. So cancel the units, and the remaining one would be ATM. So if you solve for the partial pressure of neon, that is 1 times 0.0821 times 298.15 divided by 2, that is approximately equal to 12.24 atm. So this is the partial pressure of neon. Now that you have the partial pressures of the individual gases, we will be using Dalton's law to solve for the total pressure. So again, according to Dalton's law, the total pressure is the sum of the partial pressures. So the total pressure is equal to 6.12 atm plus 12.24 atm, and the total pressure is equal to, you add the two numbers, that's 18.36 atm. And this is the total pressure, which is the answer to example 3. Now let's see the other solution to example 3. So in this solution, we will only need the ideal gas equation. So as mentioned in the previous slide, if we rearrange the ideal gas equation to solve for pressure, the equation becomes P is equal to nRT over V. So let me just copy the equation. P equal to nRT divided by V. Now the problem is asking for the total pressure. So if you want to use the ideal equation to solve directly for the total pressure, so your equation becomes P total, and for N, you will be using N total as well. So P total is equal to N total RT over V. So N total is, of course, the total number of moles of all the gases in the mixture. So there are two gases in the problem, 0.5 moles of argon and 1 mole of neon. So to get the N total, you will just add 0.5 moles and 1.00 moles, which is of course equal to 1.500 moles. So this is your N total. Now you will substitute the N total into the ideal gas equation, 1.500 moles times R, 0.0821 liter atmosphere per mole Kelvin, times the temperature, 25 degrees Celsius is equivalent to 298.15 Kelvin, divided by the volume, which is 2 liters. So cancel the units. Moles will cancel, Kelvin will cancel, liters will cancel. So we have ATM left. So if you're going to solve for the total pressure, or P total, that's 1.5 times 0.0821 times 298.15 divided by 2. And that is equal to approximately 18.36 ATM, which is the same answer that we got using solution 1. So again, there are two solutions to this problem, and it's up to you on which solution will you use depending on your convenience.